and your next 6 quarters will be based on the type of lettering that you put on your drawings. Drawing a picture, anybody can draw a square, is important. However, the lettering is approximately about 50% of the importance of a drawing. In industry, the engineer will give you a sketch for you to draw, and he is very interested in his idea being represented in a drawing, and he wants it to be very, very good. We are going to be representing that engineer. He's going to be showing your drawing in meetings, and he wants it to be good. Your opportunities for employment will be very good if your lettering is good. If your drawing is slumpy and your lettering is good, you will do well probably in interviews. If your lettering is not very good, then your chances of getting the job, still the employers out there are probably old-time senior engineers, and they want good lettering. That's what they're going to look at. We're going to emphasize all other aspects of drafting, but today we're going to talk only about lettering. Okay, so another thing we want to stress is a drawing becomes a permanent record for an industry. You can look back in drawing files from 1923, pull out a drawing file, and it's going to be a beautiful drawing. Unfortunately, a lot of our drawings nowadays are fast and dirty, and they're not as good, but you can't be as proud of them, and maybe they're not even kept by industry. So if you make a A in this course, you're going to earn it. If you make an A in this course, you're going to know how to letter. If you get out of here and you have a transcript, if you have a transcript that has a course with an A, you got another one with a B, you got another course with an A, another course with an A, the employer is going to maybe zero in on that. If it says drafting first quarter, he's going to wonder why. If it says physics, he's going to be pleased, but he's going to wonder why, because you're in the drafting technology. So this is going to kind of stand out. These will stand out, this area will stand out more. Okay? So your grade that you make it here is going to be important. We're going to be using the Ames lettering instrument, and after a couple of quarters, we're going to get rid of it. When you get through here, after 6 quarters, you won't need your Ames lettering instrument. I'll explain to you later how to use it for guidelines and constructing your letters. But just point out a few things that we're going to center on in our lecture. For instance, the alphabet. Mechanical lettering is primarily incline lettering. Incline lettering is generally about 22 degrees. Your Ames lettering is designed for that as a guide. If it's 17 degrees or if it's 24 degrees, we're not worried about it. When we get through here, we're going to be able to letter without using the Ames guide during inspection. We're going to draw guidelines by experience. We're not going to measure 1/8 of an inch for guidelines. There's a way to construct letters. An A, in high school you made an A like that. We're going to make an A like this. This is a different angle than that. This line is different length than that line. Here's your 22 degrees. Right there. This is not 22 degrees. I don't want an A that has 22 degrees on this leg. A B, we're going to construct a B, 22 degrees. We're going to put a tick mark here, one just above midpoint, and we're going to construct that B. It's going to be a block letter B. That one there didn't turn out too good. We're going to construct it. We don't want any B's like this like you did in high school. That's a no-no. Minus 2 points. A C is hard to draw, but you have to construct that C. You've got to come out and add this little bit. You have to construct it just like the guide handout I showed you. D is similar to a B. You've got to make that tick mark there. If you don't make that tick mark, you're not going to have a full D. It's going to look funny. E, F, G, G is hard to make. It's kind of like a C. We come back, here's your 22 degrees right here. Right there's your 22 degrees. You got to add that tick mark up there. You have to construct and create that G. You don't spend much time on it. But pretty soon you're going to be able to whip that G out real quick by the time you get through with 6/4. H. I don't want any H's like this. It's not right. H is just a little bit above the center. Here's your center point of your letter. It's just a little bit above. Spread that H out. We don't need H's like this or H's like this. We need H's that are spaced correctly, and this is just a little bit above center line. J is very hard to make. You come over here and you add this part to your J. You don't make a J like that. It'll look bad on a drawing. It'll ruin your drawing. Let's create a J correctly. This right here, if you finished it, it would be an ellipse. M. Come in here and put that dot right there. And then connect the points. These lines are different sizes right here. M. There's your 22 degrees. Connect that point right there. That way you get this right in the center. An M like this doesn't look very good. You're going to have to work on your O more than anything else. An O is created like that. It isn't created like this. I don't want to see any 2's like this right here. That's not pretty. This right here will not get it. You can have a little, that's fancy, but I don't want to see that. A 2, an engineering 2, is like this right here. And it's constructed a certain way. A 3. This is not a 3. This right here is. You construct and create that 3. Okay? And so forth and so on. We're not going to be using lettering instruments in here at all. You will use instruments for gears. You'll use instruments for architectural templates, rather. You'll use templates for electronics. You will not use lettering templates here. Neither will it be accepted on the job. If it is accepted on the job, then you're probably not going to reject it because you're going to know how to letter and you won't need it. It's poor practice to letter with a lettering template because you can draw a drawing. I could draw a drawing that takes y'all 8 hours, and I can draw it an hour and a half and letter in about 20 minutes. So you'll know how to letter. And CAD, we don't have to worry about our letter because CAD does it for us. However, we want to use the same style of text on a drawing. We don't want script or Roman numerals on a drawing. We want mechanical drawing on a mechanical drawing piece of work. Okay, is there any questions?
Explain the 22 degrees on the letter M that you were showing.
Okay, a letter M. Here's your 22 degrees right here.
Okay.
Here's your 22 degrees right here.
So it's not the other.
If you did this right here, that would also be 22 degrees. Okay. W did that.
I just said it's 22 degrees on the 0 on the O.
22 degrees there's 22 degrees right there. It leans. On mechanical lettering, it has to be inclined. If you get out in the industry, they want vertical, you'll get it. Okay. Exercise, physics lab exercise. We are going to look at our inductive reactants and how we can find inductive reactants by the use of formulas. I have already explained to you a little bit about finding capacitive reactants in the previous illustration. Now then, we have advanced into our technology to include the impedance. Now then, the impedance, definition of impedance, I want y'all to write this down. You're going to see it later. Impedance Everybody see this? Okay. Impedance is the total opposition to current in a circuit. Impedance is the total opposition to current in a circuit. Okay, now then, the symbol for impedance will always be in electronics the capital letter Z. The unit for impedance will be in ohms. The unit for impedance will be in ohms. In a total resistive circuit, the impedance is equal to the total resistance. Also, in a purely capacitive circuit, the total impedance is equal to the total capacitance. In a series RC circuit, the total impedance will be equal to the combination or the total of the reactance and the capacitance. Okay? Now let's look at an example here and see if we can solve for impedance. We have a problem here. Determine the impedance of a circuit that has a 34.5 millihenry coil and a 17 ohm resistor in series. And the frequency in this case will be 60 hertz. So right away, this is going to be, we're going to solve impedance problems always in two parts. First of all, we have to determine the inductive reactance, which is our X subscript L, which we studied the day before yesterday. Okay, we have to incorporate that formula before we solve our impedance problem. So let's work that problem here. The formula for finding our inductive reactance is XL equals 2 pi times F frequency L inductance. Okay, so in our case right here, by the way, we want to, let's go ahead and solve for XL. XL equals, I'm going to say 2.68 for 2 pi. We want to multiply that. Our formula has 60 hertz. Okay, and how much do we have? Let's see, millihenry. Let's convert that to Henry. Of course, we move our decimal back 3 places for the convenience of working our problem. 0.0345 Henry. Okay, if we multiply that out, the way I multiply, I want to go ahead and show 37.6.8. I've got that pre-figured already to save a little time in this discussion, times 0.0345 Henry. If we go ahead and multiply that out again, we would get something like 12.9996 ohms, since our units for the inductive reactance is also in ohms. We'll solve for ohms. And in engineering, we always simplify, if we can, to a workable figure, numerical figure in other formulas, say 13 ohms. So right away, what have we done? We have solved for our XL. Now our formula for finding impedance is going to be, let me write it right here, Z equals the square root R plus XL squared. We know what our resistance is from reading our worded state problem. Our resistance is 17 ohms. We just now solved for our inductive reactance, X subscript L, and we'll square it. So let's go ahead and plug those values in. Right away, we want to solve for Z, our impedance. L, we said from our problem, is 34.5 million hertz, or why don't we say 0.0345 hertz for the convenience of working. F, small f, we learned that already, is our frequency in hertz, 60 hertz. And of course, our resistance we said was 17.0 ohms. These are our values. Let's plug our values into our impedance formula. Simple enough. And let's see what we get. And change colors here real quick. So right away, what are we solving for? Z equals the square root of, or resistance squared plus, we know we have 13 ohms squared. Where do we get it? Right here, from our inductive reactance solution. Let's go ahead and factor this problem out. The square root of our ohms was 17 ohms. 17 ohms. We want to square that times, under the radical, 13 ohms squared. Let's go ahead and combine terms. Under the radical, okay. I want 289 ohms plus, factor that out squared. I'm going to get 169 ohms. Okay. Combine terms. Under the radical, I'm going to have 458 ohms. I want the square root of that. If we take the square root of that, we're going to have Z, impedance, is going to equal to 21.4 ohms. Do you have any questions on how we arrived at this two-part solution to this physics problem? Any questions on it?
Where did the 21.4 come from?
21.4, that is the bottom line, that is our impedance answer for our stated question right up here was determine the impedance in terms of.
But where did we get it? I got lost someplace.
Okay, let's back up. I don't mind backing up here. So right away, we went ahead and we used our impedance formula, which was this one right here. This is in your book. It's on page 533. Our impedance equals the square root of, we have our reactance, and then we have our inductive reactance. Squared. Plug our values in, just like this right here. Simple. Here it is written out for you. Solve for Z, and we come up with 21.4 ohms. I want you to remember this. I want you to know how to kick one back similar to this on the test that we're going to have Monday. Monday, I want a couple of these problems on there. I want you to also brush up on your decimal places when we talk about milli. I want some pico decimals in here too. Just like I told you, memorize that list of values. Okay, any more questions? At the end of chapter 18, for assignment, let's work problems number I want to work problems number 15, 16, 21, and 22. Okay? Work those problems. Those are impedance problems. And then give it back to me. I want this. I'm going to give you a little slack on this since I gave you homework in theory. I want this Wednesday. Okay? Time for the bell.
What kind of symbols are these things called?
those are tolerance, dimension tolerance symbols on the page. Position, they're called form and position tolerances. Okay. Okay, here's an example of concentricity tolerance or position. You have a shaft here, you have this diameter here is datum A. This diameter right here is to be in two circles are said to be in concentricity with each other if they both have the same spin point on them. So that's what this right here indicates, that they're exactly in line. No, we don't have any, but just one, well, okay, 1/10, say, okay, of misalignment here. It's allowed that much, okay? We're going to go into this a little bit more tomorrow. See, I think there's one or two more I want to point out though before I shut her down. Two inclined lines like that means parallels. And I guess if you had a surface like this right here, you could point to this surface. Parallelism 1/10 A. This would be parallel to this right here. It wouldn't have, it could not be like that very much. It could be like that 1/10. Okay? That's how this is used. That's how all these are used, just like that. This thing can go crazy. You can keep adding on to it. This, you can have a, this right here is your first datum, second datum, third datum, so forth and so on. You can have a bunch of these things down here. This might be B. Depends on what your picture is. You might have a C down here, so forth and so on. These things you can, some of them real long. Okay. Okay, I guess probably have a fairly good understanding now of tolerancing and how they'll be related to machined drawings. Are there any questions that we discussed before or anything? Michelle, what?
You can keep adding boxes on that one related to the same.
Yes, you can.
compare that with the A and the B and the C.
Yeah. Of course, they'll get much more busier than this on the drawing. You can have a drawing that's just loaded down with.
Do you have a drawing like that you've done?
Yeah, I do. I may try to bring it on to you. Okay. You see, besides all these on a drawing, you've got finish marks.
Yeah.
Now this is going to finish us up today, probably on tolerances, but tomorrow we're going to take up a continuation of the same type of machining, and we're going to get into machining surfaces, okay, which kind of goes hand in hand with tolerance. Okay, so does anybody have any more comments on it? Anything? Yeah.
And you're running like BMC up there, do you draw like construction lines coming down like that? No. How you did the, after you drew the object, you drew the other, the line coming down?
Right here? All this one up here?
No.
Down here?
When you drew the box like again, under it, yeah.
Like right there?
No, when you drew the box under it again.
Like right here?
Yeah.
Yeah, what about it?
Do you draw that when you're drawing your, you have
Well,
drawn?
this one here is a figure, okay? It's a
Uh-huh.
continuation of this figure here, maybe.
Okay.
Okay? And yes, they all have a little box on it, like
So
this
you
right here.
continue the figure?
Yeah.
Okay, that's perfect.
Correct.
Would it be just as correct up in the box with A dash C, it says A, B, C, and all of those separate boxes?
No. You like that?
Even if it went on down to
Yeah.
C?
Yeah, anybody can go to A, A, B, B.
And then you would say, really?
Yeah. Oh, yeah, it's gonna keep going.
Oh, wow.
Yeah, you'll find applications, maybe not quite that crazy, but you'll find some applications where you'll have these things where it's strung out, okay? Bradley, could you have several on a, like on a crankshaft of a automobile? Could you have several data points? You could, all kinds. You might even have all of these. Good. Could have that one right there. This one. That one there. Straight this. So you could have even this one right here. Yeah, drill on the end of it, maybe for a bolt or something. You can have just all kinds. And that could be just really, you have all of these, you have 2 dozen of these. Okay?
You take one of your car. Would you have anything like,
Beg pardon?
if you had anything like, tolerances like, might deal with chemistry or something, if you were working with something like that? But it just machine.
Machine, yeah. Mostly your machine. You're gonna have reference points and data points on other types of things also, another, in archaeology, architectural and structure, you'll have reference points, but it's a different scope, okay, than what it is on
One
machine.
that's limited.
Huh?
One that's limited.
Yeah.
An example of visual continuation of an object like that?
Another illustration of more.
Yeah,
I don't have time to show you on the board, but you can look in your book.
that's what I'm saying. Is there-
Yeah, there's some in there. You might look at the index under tolerancing, but I notice in the books they go 4, 5, or 6, or 7, just, they really get carried away. Okay? Steve, what kind of drawing, engineering drawing would most likely have something like this? Machine drawing, that's right. Absolutely, good, you did well.
Yeah.
guess I'll,